in this section, we're going to introduce the idea of instantaneous rate of change. So we've talked about average rate of change and average velocity, in particular in that last section. We looked at average velocity, right, over a time interval. So when you have average rate of change or average velocity, it's over some time interval, right? We have to choose an interval. Now, when I'm driving down the road, I can glance down at my speedometer and it'll tell me what my velocity is, what my speed is at that particular moment in time, right? I'm not, I just look at it, right? And it tells me a velocity. And I don't have to like look at it once and then look at it again and do any kind of calculations in my head, right? It's telling me at that instant in time, this is the velocity, this is my speed. All right. And so we want to introduce that concept here, the idea of finding a velocity at a particular instant in time instead of over an interval. So let's take a look at this next example. Now this might look familiar. This is the same scenario as we had in example 1 of the last section, where we have a watermelon that's dropped from a roof of a 125 meter tall building. And we're given the function for the distance from the ground over time, right? 125 minus 5t. So the first task here is just to sketch the height over time. Now we did that in the last section, so I'm going to go ahead and sketch that for you really quickly. All right, so there I've sketched the curve for you, and I've labeled the points because we might need that information later on. Actually, I just realized that this is supposed to be 145. So let me fix that quick. 140, or sorry, 4,45 is what I have. All right. All right, so the next question is just asking us to find the average velocity between 2 and 3. Now, if you remember, to find that average velocity, we're just going to find the slope of the line between those 2 points. Okay, so there's my line, and oops, what happened there? Escape. I was trying to get rid of that. Okay, so there's my line. All right, we want to find the average velocity, right? So it's going to be the change in y over the change in t. And I can just take 80, right, minus 105 over 3 minus 2. So I get a negative 25 over 1, which is, I'll write it down here, negative 25. And the units are meters per second, right? Because my distance from the ground is in meters and my time is in seconds. All right, so that means my average velocity is in meters per second. Now it's negative because the distance from the ground is decreasing, right? It's getting closer to the ground. It's being dropped. So that's why it's negative. On the graph, show the average velocity. Okay, we did that already. I drew the line between those 2 points. The slope of that line is the average velocity over that interval. All right, so here's the new part. So we're doing something similar to what we did before. We want to find the average velocity over these intervals, but you can see now that the left-hand side of the interval in each case is 2. So what I'm doing here is I'm finding average velocities that are getting closer and closer together. So initially, what I'm doing, let me draw these lines on here. I'm going to find the average velocity between 2 and 4, right? And then I'm going to find the average velocity, let me see what's going on here, between 2 and 3, which I already did. And then, let's see, what's the next one? 2 and 2.5, 2 and 2.1, 2 and 2.1. So I'm just taking shorter and shorter intervals. I don't even know if I can show that. 2 to 2.5, will be in here, and then I'm going to just keep taking shorter and shorter intervals. Now I don't have to use the graph because I've got the equation. I've got the function, right? We know that I'm going to rewrite it down here. Y is equal to 125 minus 5t squared. Okay, that's the function. So I'm just going to use the function. Plug values in. All right. So let's first of all find this first one. I'm going to do the calculation over here. So when t is equal to 4, I'm at 45. So 45 minus t at 2 is 105. And then I'm going to divide that by 4 minus 2. Right? When I do that, I get a negative 30. Okay, so this value right here is a negative 30. Next interval, we just did that one, so I'm just going to write it down, right? So this is 25. All of these are going to be in meters per second. I could put meters per second on here if I want to, but it's going to be meters per second all the way down. All right, let's look at between 2 and 2.5. Now, what I need to do is find the value of y when t is 2.5. So I'm going to take 125 minus 5 times 2.5 squared. All right, if I do that, I'm going to put that into my calculator, and I got 93.75, right? That's my the value of the function. That's my distance. That's the distance above the ground when t is 2.5. And I'm going to subtract 105, and then I'm going to divide that by 2.5 minus 2. Okay. Do that calculation and I get a negative 22.5. Negative 22.5. All right, I'm just going to do that all the way down. Just going to plug in the value here on the right-hand side of the interval and subtract 105 from it because that's my value at 2. And then I'm going to take it and divide by the time interval. All right, so when I do that for each one, I don't know if I need to write out every single one. I'll write out one more. The next one I get 102.95, right? That's the value at 2.1 minus 105 over 2.1 minus 2, and then I get a negative 20.5. Negative 20.5, okay? I'm just going to do that for each one of those. Now, when I do it for 2.01, right now I'm taking a really small interval between 2 and 2.01. I do that same calculation and I get 20.05. I do the same calculation, now it's between 2 and 2.001, right? So I'm just taking smaller and smaller intervals, closer and closer to 2. 20.005. Okay, I don't know what happened up here. Rewrite that. All of a sudden it jumped on me. Negative 22.5. All right, so there are my average velocity calculations. And what I've done is I've just taken smaller and smaller intervals. So I'm getting closer and closer to 2. I could do another one between 2 and 2.00001, or between 2 and 2.000000001. I could do it. I could get as close as I want to, and I'm going to get better and better estimates of what my instantaneous value for velocity is at t equals 2 seconds. So based on what we have, what is your best estimate of the velocity at t equals 2 seconds? Well, it looks like, as you know, these values, these endpoints of the interval get closer and closer together, it looks like the value is getting closer and closer to a negative 20 meters per second. Okay, and again, it's negative because it's falling. It's getting closer and closer to the ground, so the distance from the ground is decreasing. Okay, so that would be my best estimate, and that's what instantaneous velocity is all about. The instantaneous velocity is defined to be the limit of the average velocity over shorter and shorter time intervals, all right, containing whatever the time interval that we're interested in is. So up here we were looking for the instantaneous velocity at t equals 2 seconds, and so if we just look at what the limit is as t approaches 2, right, that time interval gets shorter and shorter and closer to, you know, as the endpoints get closer and closer to being just 2, right? Then we get the instantaneous velocity. All right, so that's the idea of instantaneous velocity. And we're talking about the limit. This idea of a limit is a key concept in calculus, where we can't go there, right? Because if you think about what we're doing here, if I just put in an interval between t equals 2 to 2, well, I'd be dividing by 2 minus 2, right? Because my time interval is 0, right? The difference in time is 0, and to calculate average velocity, you end up dividing by 0. So we can't go there directly, but we could sneak up on it. So that's the idea of a limit. And instead of going there directly, we're just going to sneak up on it and see what's happening as we get closer and closer and closer.